Hackers and hackerettes, welcome to a new video in our TryHackMe pre-security software basics playlist, I guess you would call it. And in the previous video, which I do recommend that you watch if you haven't, we talked about how information, or specifically numbers, are represented in the computer. Today we're going to be talking about data encoding, which learning how computer encodes characters from ASCII to Unicode's UTF, okay? So if you haven't watched the previous video, again, please do, because you'll be missing a lot of context. All right, let's get started. In the previous room, you learn how numbers are represented in the computer as binary digits or bits, and how these bits can be grouped into hexadecimal digits. We also explored how to express colors using numbers. Now, if everything is stored as numbers, how do we convert them to letters, punctuation, and emojis? I mean, since we already represented colors, we can easily represent characters just as numbers, the same way we did with colors, you know? In this room, you will learn that characters are just numbers with agreed meanings. That agreement is called an encoding. Have you ever opened a document, visited a web page, or downloaded movie subtitle files only to see the file appear as weird gibberish, just like that? One reason for that is the user who saved the file and the user who opened it are using different encodings, okay? This is cool. So you can see here the word al-diwan. This could come up as meaning something related to poetry. Yes, I do read Arabic. I know Arabic. It is my main language. So al-diwan comes up like poetry, a piece of poetry. And this is probably Arabic, but which was encoded poorly, or not encoded poorly, but rather the viewer is using a different encoding rather than the encoding that the text was written in, you know? So I probably they were using ASCII, but it should be converted to UTF-8 or something like that. Anyway, representation is the idea that data lives as bits and numbers in memory. At the same time, encoding is the specific agreed upon mapping between numbers and meanings, such as which number corresponds to the character A. In text, each character, like Q, 5, or exclamation mark, is assigned a numeric code. So a string becomes a sequence of numbers that the computer stores and moves around just like any other data. So computers only understand zeros and ones. These zeros and ones can be used to represent numbers, represent colors, represent text, and just anything else. Like only zeros and ones are used, and we can use numbers to represent characters, and then we can use zeros and ones to represent numbers that represent this text that we are looking to save or work with on a computer. I hope that makes sense. Upon completion, ASCII, Unicode, UTF-8, 16, and 32, how emojis is encoded, or emoji, singular, and what causes weird gibberish characters. All right, let's get started. Essential to finish the data representation room, which we did in the previous video. This is why I keep stressing that you should watch that video first. Okay. ASCII. We already learned that digital computers only understand zeros and ones. Starting from 0 and 1, how can we save and display text? For example, how can we save the text TryHackMe in a file? What will such a file contain? To be able to answer this, we need to agree on what bits represent T, what bits represent R, what bits represents Y, and so on. Let's say that we all agree to represent T with the following stream of bits: 0, 1, 0, 1, 0, 1, 0, 0. Then all computer systems should store T the same way. And later, when a computer encounters this, it will recognize it as T. Of course, we need to do this for all letters in the alphabet, digits, and special characters. And not only the alphabet of English, by the way, because, yeah, while everything started in English, computers exploded worldwide. Say you speak Arabic, and then you need the Arabic letters alphabet in there as well, which are completely different from English. You say Russian, you say something like Greek, which also has completely different alphabet from Latin-based alphabet. This approach requires a standard that computer manufacturers, designers, and programmers agree to adhere to. One of the earliest standards for English letters was ASCII. Okay? ASCII stands for American Standard Code for Information Interchange. American Standard Code for Information Interchange. And it is an early character encoding from 1963 that uses numbers 0 to 127 to represent English letters, digits, punctuation, and some control characters. Remember that A stands for American, as this will come in handy later. I think they're foreshadowing that it was only used for English and started for English characters only, and that we need to represent other alphabet. So I kind of like foreshadowed there because I know a bit about encoding, but they are also foreshadowing. As you might have noticed, the original ASCII was limited to 7 bits. ASCII acts as a small bilingual dictionary between text and numeric codes. Consider the following samples from the original ASCII table. Since that table has 128 entries, we only made a brief selection to give you an idea of how things are represented in ASCII. Yeah. So the decimal 48, hexadecimal 30, the binary is this, symbol is 0, description is 0. Okay. So the 0 is being represented like that, I guess. And then you have the 9 represented like this. You have X, you have things like that, E backslash and whatever. So there's like a table of all characters. We don't care about that. We don't need to memorize any of these because computers can super simply just, or even just a small Google search would give you every result you need. So we'll not really be memorizing it, but we will be understanding how and why things are represented this way. There are several things that you can observe. First, letters are in order. If you know the hexadecimal or the decimal number for B, you can figure out the decimal number of A, C, and later lowercase characters. For example, A, B, and C are assigned the hexadecimal numbers 61, 62, and 63 respectively. So A is 61, B is 62, C is 63, and same for uppercase letters A to Z and digits 0 to 9. When using ASCII encoding, a computer system reads 41 in a file and displays capital A on the screen. When it reads 42, it displays capital B, and so on. So now you know that lowercase and uppercase are represented differently because they are different characters. Okay, I should rephrase it. They're not really different characters, but they look different. So this is why they are represented differently on a computer. Like lowercase has different values than uppercase. Okay. So lowercase starting from 61, lowercase starting from 41, I guess. Yeah. Secondly, each character has its own ASCII. For example, the open bracket here is represented by the hexadecimal 5B. So TryHackMe in ASCII. Let's say you open a text file, write TryHackMe, and save it as file.txt. How will the file look on the bit level? Let's find out. If you are interested in seeing the storage in disk bit by bit and assuming that is ASCII, you will see something similar to the following. 0101010000. Of course, I'm not going to read all of that. Obviously, this is not readable by any human being. Actually, it is by us. If we can convert this to its hexadecimal, and then we can use the above table, we can read that. But anyway, these are the exact binary representations of all letters in the TryHackMe followed by a new line. When you open this file, your editor will read the bits and display the following characters. The \n is a new line that you get when you hit the enter key. Because reading binary numbers is cumbersome and error prone for us, we prefer to use hexadecimal digits. As you remember from the previous room, we group 4 bits into a single hexadecimal digit. Our file looks like this in hexadecimal. Much easier than definitely the binary here, but still not as fluent as TryHackMe, you know? If you want to look up the decimal representation, it would be as follows. So this is hexadecimal, and this is just decimal. However, it is uncommon to use decimal digits. It is more common to use hexadecimal digits when we want to show the bits. You can see the attached static site yourself to experiment more. I don't know where that is. Maybe it's below. Yeah, there it is. European languages. ASCII provided a way to encode the English alphabet. However, we need an encoding to support other European languages as well, such as Spanish, like the little N here, and the flipped question mark. The German, I think this is an S in German. I'm not sure, actually. I might be incorrect. But you have the Polish, you have the Czech, and Romanian, to name a few. ASCII, also, it's not only... Why are they only European language? We have, like, the Arabic language as well, which is, like, African. Or is it African? I guess Arabic originally I actually don't know. If we're gonna say Saudi Arabia, then we're probably gonna say Asian. Originated in Asia. I'm not sure. Anyway, ASCII uses 7 bits, and with an 8 bit, we get 128 more characters to cover. However, the reality is more challenging. The additional 128 characters are not enough to cover all the letters of the European language. The ISO IEC 8859 series international standards created several standards. Each standard covered each set of languages. So you have ISO 1 for Latin, ISO 2 for Latin 2. So this is Western European language. Central and Eastern, like Polish and Czech, Hungarian, Croatian, Romanian, and Slovak. We don't care much about that, honestly. In other words, if your document is saved using ISO 1 and later read and displayed as if it were saved using ISO 2, non-English letters are likely to be displayed differently. And use the answer to follow. Okay, what is the ASCII code for the decimal character at? So the ASCII is... What? Oh, in decimal. I didn't read that correctly. What is the character that has the ASCII code of 35 in decimal? Hashtag. What is the name of the character that has ASCII code of 7? The name of the character that has the ASCII code of 7. So what is the ASCII code exactly? Is that Bell? Yeah, it is. So we got that correctly. If you don't know what the bell is, I think bell is the character that used to make a bell designed to trigger an audible beep or visual flash on a device. Exactly. So whenever you have, but I have it disabled, so I cannot show you. But if you open up your terminal and then you see this flash right here, I don't know if it's appearing on code or like on recording. I think it is. And then there's usually like a bell, tin, 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 you know? This is what causes this thing to show, which is this bell character, which is ASCII code of 7. Cool. Let's go to Unicode. We learned that ASCII is a 7-bit standard that defines 128 characters covering English letters, digits, and basic punctuation. We also noticed how ASCII, with its 7 bits, did not have room for characters such as these ones, or B, which is B in Arabic, by the way. Using 8 bits extended ASCII. Extended ASCII tried patching this with regional variants, ISOs, and Windows, among many others. But this caused chaos. For example, if the sender writes phi or phi using ISO 1 or Latin 1 encoding, and the recipient opens a read document using ISO 2, they will see this. Hence, it is clear how opening document requires us to use the same encoding used when saving it. Otherwise, various characters will not be displayed correctly, or even more confusingly, they might be incorrectly replaced. Yeah. So you write phi or phi, and then you open and see this, you'll think that there's nothing wrong, and this is the intended thing, even though this is the intended thing. This happens because different encodings use the same values to represent different data. So for example, Latin 1 used, let's just say hypothetically, used the number 1 to represent phi. Then in Latin 2, they use number 1 to represent this character, which means that, of course, they will be different. I'm calling this phi or phi because this is how it is in Greek. Phi characters. Why is it bringing language? Oh my god, phi character Greek, man. Oh, phi. Yeah, that's called phi. Okay. This is what I was talking about right here. I don't know if this is actually different. Let's copy and paste this. Maybe I'm incorrect. The character is the Danish and Faroese. It has several key meanings. Scandinavian is standalone vowel representing a mid-front rounded vowel. Okay, so it sounds similar to U, bleu. So yeah, I guess I was incorrect. This is not phi or phi. This is a different character. My mistake. But it looks like the phi in Greek, so. Anyway, replacing that, let's go to, unlike English, which has 26 letters and needs 52 characters to cover up uppercase and lowercase, 26 times 2. Arabic needs more than 250 characters to cover its various ligatures and diacritics. I don't even know what this word means. Meaning, let's see what it means. Symbols such as dots, lines, or squiggles. Okay, yeah, this is what it means. Moreover, the number escalates rapidly when considering Japanese and Chinese. In Japanese, 2,136 kanji, logographic characters, are considered daily use characters, as mandated by Japan's Ministry of Education. In fact, the JIS X0208 standard defines 6,879 characters. That is a lot of characters. In Chinese, educated natives recognize around 8,000 characters. Furthermore, the JP whatever defines more than 87,887 Hanzi, Chinese characters. And still, we have not considered the encoding emo icons or emoji. Okay. Sheesh. In other words, it is essential for both the sender and the recipient to use the same encoding. Moreover, we need an encoding that can include all the characters from all languages. This situation brings us to Unicode. Unicode is a universal character encoding standard. It assigned unique code points to characters from all modern and historical writing systems worldwide. Unicode supports the interchange, processing, and display of text in diverse languages. In other words, we don't need to worry about picking a specific encoding standard that is compatible with the language we are using. Furthermore, this makes it easy to use different languages in a single file or message. And most importantly, because this is a standard that fits all, we don't need to worry about the encoding used by our original author, as they will also be using Unicode. Unicode is a character set standard that assigns a unique number to every character across all languages. Examples. This is the Latin A. This is the Greek omega. I think this is an omega. Yeah, so it is omega. Now, when you copy it, it looks like this, but it is this. So one of them is capital, I believe, and one of them is a small letter. So this is an omega, yeah. And you have the Japanese hiragana. I don't know what this is. I cannot read Japanese. Oh my. English. A. Cool. Unicode 17.0 is currently the latest version of Unicode standard. It defines close to 157,000 characters. Almost 4,000 of them are emoji sequences. Jeez. UTF-8, 16, and 32. Because you will encounter UTF-8, 16, and 32, we will briefly cover them without going into too much depth. What you need to know is that UTF-8 is very common on the modern web. It encodes the Unicode points into 1 to 4 bytes dynamically. In other words, it decides on the number of bytes based on the character complexity. ASCII characters, UTF-000 to UTF-007F, use exactly 1 byte, identical to the original ASCII, ensuring seamless backward compatibility. Non-ASCII characters like omega, this one use 2 bytes, while complex scripts or emoji like this requires 4 bytes. Okay? So this flexibility allows us to cover the Unicode standard without wasting bytes. Yeah. So example, if you unify everybody to use like the highest bytes available, so 4 bytes, something as simple as the letter A in Latin, which just needs 1 byte. So for example, like this, or actually all the ASCII characters, like from the capital A to capital Z, and including lowercase a to lowercase z. Anything that exists in the ASCII characters will use 1 byte. If we unify everything to use like the 8 or the 4 bytes right here, then we'll be wasting a lot of bytes in this, and we'll just be consuming more memory than we need to store something that can be represented in less memory. Okay. So this is UTF-8. UTF-16 takes a different path. It uses either 2 or 4 bytes per character. Common characters like most Latin, Cyrillic, or Chinese Hanzi fit in 2 bytes. However, rare ones like emoji or ancient scripts require a pair, 2 16-bit units totaling 4 bytes. For example, the letter A is encoded as this, while the emoji fire needs 2 and is encoded as this. Finally, UTF-32 is the simplest but also the most wasteful. Every Unicode code points use exactly 4 bytes. So everything uses 4 bytes no matter what it is. So this is also a waste of memory, of course. Let's explore a few more examples. This symbol, one of these Chinese characters that appear on offensive Linux distributions, such as Kali, which means dragon. In Unicode, it is this or this, depending on whether it's 16 or 32. The smiley face is nothing more than this in UTF-32. For a computer, that's literally this. So your smiley face emoji, the one that you're happy about, this is what it is in computer. The Japanese letter 2, which some people use as a smiley face in some regions outside Japan, has the code this or this, depending on whether it is UTF-16 or 32. Te, which is the Arabic letter ta, or ta, is the correct thing for it. Ta, which is the third letter, so alif, be, te, or ta, which is the third letter in the Arabic alphabet, similar to a T in English. And some people use it as a smiley outside the Arab world. It looks close enough to a smiley face from a Unicode perspective. That's this. The Black Knight in chess uses the Unicode this. In other words, the computer reads this and shows you a Black Knight, thanks to Unicode. Okay? We have created a static site to help you look up characters and explore new ones available in most standard fonts. Click the view site. What is the UTF-32 encoding of this? Let's see the 32. There it is. Go away, man. What is the UTF-16 encoding of this? Note that this and this are 2 different characters. Wow. Wow, man. How do I even copy this? Okay, there we go. So UTF-16. What is the character that has the following UTF-16 Unicode encoding? If I can... Copying is so weird in here. It is the teacup. What is the character that has the following UTF-16 encoding? The Black Knight. Or the White Knight, I guess this one is. I don't know. So yeah, we've been going through Unicoding and stuff, or encoding, including ASCII and Unicode. We went also through UTF-8, 16, and 32. And if you don't understand anything about this, I'm just going over it like skimming in case I missed anything. I think we got everything. So conclusion, in this room we learned about ASCII and its limitations, and about Unicode and 3 encoding standards, UTF-8, 16, and 32. We explored how Unicode enables us to cover not only the world's languages, but also symbols such as chess pieces and emojis. If you are curious to see how computers manipulate data, join the Python demo room. Coming soon. Okay. So we finished this bad boy, and we will see where we will get next. And we are going to get into Python. I don't know why Python has a JavaScript backend or like code here or logo, but yeah. If you've enjoyed this room, give me a like, give me a subscribe, and give me comments below about how you think these videos are doing. If you think they're good, let me know. If you think they're bad, also let me know. Any constructive criticism is always welcome. All I'm trying to do here is just give you guys a comprehensive knowledge base, because I learned from the community. All I'm trying to do is to give back to the community. Thank you for watching, and I'm looking forward to your feedback. See ya.